first parallel session. It will be the session on complex systems, the first part of the complex system session. In this session we will hear about networks, a network view, and more from maybe from computational science and from the information theory view, from information theory science, if you like. And so I'm happy now to announce the first speaker, Tina Eliassi-Rad. She's a professor of computer science of Northeastern University, Boston, Massachusetts. And her research is rooted in machine learning and data mining, and especially applied to network systems using massive amount of data. She's working in theory, algorithms, and applications, and some of the applications you can even get through open source software. So now in this talk, she will talk about learning and inference in complex networks.
Thank you. So thank you very much for coming, and thank you for inviting me. This is not my usual audience. As it was mentioned, I'm a computer scientist. My background is in artificial intelligence and machine learning. And about 2004, I started working on complex networks. So when you think of a network, think of nodes and links, or edges and vertices, and what is complex about them is the topology, or the structure of it. Since I'm not going to be talking about dynamical processes on networks, I'm going to be using terms like networks and graphs interchangeably, and nodes and vertices interchangeably, and edges and links interchangeably. So if that bothers you, my apologies from the very beginning. So complex networks are ubiquitous. If you haven't drank the Kool-Aid, come see me afterwards. Right? So you have things from technological networks, like the internet. You have information networks. What you're seeing up there is a map of science, where a node is a journal, and a link between two nodes says that a paper in one journal cited a paper in another journal. This appendix over here is humanities. This is social science. This is math and computer science, and it's actually a globe. So you can spend a lot of time playing with this. Is very fun, especially, for example, for funding agencies. If they want multiple disciplines to link to each other, you can see, who's publishing at the borders of these disciplines. And of course, there are social networks like the Facebook network.
What's that?
I forget. I think maybe something about medicine. I'm not quite sure. Well, essentially the way it's depicted, right? So visualization can lie to you, right? So this is a globe, right? So I could have made the 3D into a 2D in a different way.
Yeah,
so you
have no links from purple to yellow.
There is actually links. Again, here is a pink one that goes around. But I don't want to get stuck on this. You can go to Map of Science and spend months on it. It's lovely, and right. So anyways, moving on, there's social networks. So they're called information networks because a node contains information, like the World Wide Web is an information network because the node contains information. There's social networks like the Facebook network, and then there are biological networks like here's a food web of who consumes whom in terms of animals. So the problem I want to talk to you guys about today is node classification in complex networks, specifically within network classification. So you have one network, and for some of the nodes, you know something about them. Think of it in terms of I know a state about them. I know whether you're a good guy or a bad guy. I know whether this paper is about differential geometry or not, that kind of things. And my goal is to assign labels to all other nodes. So here, you know something about the black nodes. I am not telling you what the labels are, it's just that the black node means I know something about that node. And then all the yellow ones are something I don't know about them. I don't know their state, and I want to be able to infer it. And there's lots and lots of applications of this. I already said fraud, or the topic of a research paper, and so on and so forth. So if you want to do learning, you have to rely on some dependencies that you're either going to learn or you're going to assume. In a complex network, it's relational dependency. So basically the fact that my label and my neighbor's labels are dependent on each other. And so we see this a lot in real-world complex networks. So we're in Belgium, and a lot of fraud detection happens here. I actually worked with the Belgium Social Security institution here with some of the colleagues at KU Leuven, and one of the things that we saw was in a network of company to company, so a node is a company and two companies are linked to each other because they share resources, that we saw a lot of homophily. This idea that if I'm a fraudulent company, I'm going to have more fraudulent companies around me than not, and here's a snapshot of that. And so there are two types of common relational dependencies. One is called selection, which is the probability of two nodes A and B having links to each other is more given that they have the same class label. This is greater than the prior probability of them just having links together. So here an example would be, given that you and I both like Apple, it's more likely that we will be friends than just the prior probability of us being friends. And then in terms of influence is that given that we're friends, the probability that we both like Apple products is higher than just the prior probability of us both liking Apple products. Now, common is not always, so there are cases in which you have, this is the complete opposite, we call it anti-homophily, where the nodes that are around a particular node do not have the same label. So again, back to our problem, before I move on, I have a network, and for some of the nodes I know their state, but for a lot of them I don't, and my task is to learn a model and infer what's going on with the rest of them. And so a standard machine learning approach would be to construct features and actually learn this relational dependency. And so one way that you can do is you can say, well, maybe I have some contextual information on the node itself. The example here is a network of phone numbers. So a node is a phone number, and a phone number calls another phone number. And maybe for a phone number, I know the carrier or the plan of the phone number. And maybe there is some dependency between the carrier or the plan and some fraud activity. The next one would be relational information, and this is where I look at my friends and I aggregate over them. And I say, for example, what is the mode among the carriers of my neighbors? Or, you know, what is the proportion of my neighbors whom I have labels for who are fraudulent? And the last one are topological information. These are basically, again, features that I'm going to extract. And like a good machine learning person, then I'm going to build a model on these features. For physicists, these are variables that you observe, right? We're basically doing the same kind of a thing, an experimental physicist and a machine learning person, where we observe the world, we extract some features, some variables. With physicists, you know, it's a mathematical model that describes the world. With machine learning people, it's a statistical model that tries to predict. So for topological information, you can get, for example, how many other phone numbers did I call, or how many triangles do I have around me. That is, how many of the phone numbers that I call each other. And these are interesting. So there was a study on some phone call data in a European country that I will not tell what it was, but for example, there were a phone call activity between two phone numbers that was in the thousands in one day, and then they disappeared. Both phone numbers disappeared. So that seems kind of odd, right? So these are features that you can extract and look at. So what are some of the challenges in this kind of a setting where I want to find labels or states of nodes? One is attribute sparsity. For privacy reasons or other kinds of reasons, I may not know what carrier or what plan you have on your phone. The other one is what we're calling link sparsity, which is that, again, for privacy reasons or other reasons, perhaps I haven't observed how many phone calls you have made and to whom you have made them. And the last one, which is more of a interest to machine learning people, is the class label sparsity, where I have this phone call network or I have any other complex network, but I don't know the value of a lot of these states. So a lot of the nodes actually don't have labels. So what would I do in that case? So why would I care about label sparsity? So during training, when I'm actually trying to learn a model, one of the problems is that if I don't have enough labels, then I can't learn the dependencies, right? So I'm sure you have all heard about deep learning. Well, deep learning models won't work if you don't have enough training data, right? And also, even when a node itself is labeled, maybe a lot of its neighbors isn't. And so you want to have the information about the neighbors. And then during testing, you may not have, so this would be during inference, you may not have enough labels to actually seed the inference process and, for example, have a value for a feature that is neighbor dependent. So what are some of the popular existing approaches here? One of them is collective classification. The idea is that I have this complex network, I'm going to treat it as a whole, and what I'm going to do is I'm going to solve a combinatorial optimization problem where I'm going to infer labels for everybody the best I can. And there are lots of popular approaches here, some of them stolen from image segmentation. I'm going to talk about the iterative classification algorithm and relaxation labeling. I won't go too much into give sampling and loopy belief propagation. Belief propagation, you may have heard of it. That was what got Judea Pearl his Turing Award back in the 1980s. Now, one of the problems with these collective classification, especially if you have sparsely labeled networks, is that they are prone to hallucination. So where if my label depends on the labels of my neighbors and there are not that many labels, then you can label everybody the same label and you won't do very well. And so approaches to solve this problem of I'm at this macro level and I want to do this combinatorial optimization algorithm is what's called, so one was by Luke McDowell, which was this idea of cautious collective classification, where I'm going to be cautious in terms of using some predictions. I'm only going to be using the ones that I feel certain about. And then we had some work with Vrije, who was a PhD student at KU Leuven. She's at SAS now, where when we are in these kinds of settings, we're going to do active inference. Active inference means that for selected nodes, I'm going to go and ask information from somebody. And then if I get an information, then I can weigh the edges properly in terms of how this propagation will get forwarded. The other one is semi-supervised learning. Semi-supervised learning is extremely popular in machine learning. This idea that I have some data here for us as a network. Some of the nodes are labeled, a lot of them aren't labeled. I'm going to use all of that information, including the unlabeled data. The problem with semi-supervised learning is that it usually relies on relational dependency being high, and also it can be prone to biases, both in terms of learning and inference. Part of it is because the distribution of the labels during training and testing could be different. There's a nice set of slides from my friend Jennifer Neville, who's a professor at Purdue, on this, which I won't, on this topic, which I won't be able to go through given the time constraints. So these are two popular approaches: collective classification, this idea of combinatorial optimization over the entire graph, and this idea that, well, I have a lot of unlabeled data, I'm going to somehow use them. And so they have issues in that semi-supervised learning, as I said, it relies too much on the relational dependency, and it's very prone to the biases that you get both during learning and inference. Here I'm showing you this network where on the x-axis there's some data sets, on the y-axis is the area under the RSC curve with, sorry, I have a little cold, so that's why I sound a little nasal. So it's the area on the RSC curve with 50% of what we're calling the core nodes labeled. These are the nodes for which I have labels for, and I'm going to remove 50% of them to do some experiments. And so the green and the purple lines are methods that are semi-supervised learning approaches, and they don't do very well where you don't have a lot of relational dependency, this idea of anti-homophily. So they really rely on this like being attracted to like. And then the collective classification approaches have this problem that if you don't have enough labels, then they're not going to do very well. So can we come up with one approach where it can span all of the different data sets and the characteristics that they have? So I want to be able to handle sparse labels and the various amounts of relational dependency. And so I'm going to talk to you guys about this thing called ghost edges. And so let's see how that works. So whenever you have label sparsity, the standard idea is that I'm going to do something like propagation. So here's a network. I have some of my nodes that are labeled, pluses and minuses here, binary classification. What happens is that the nodes that have labels will propagate the labels to others. The nodes that weren't labeled now get labeled, and then this thing continues until the node that you're interested in now has a label. And so the idea is that we have plenty of neighbors, but too few of them are labeled. So what I'm going to do is I'm going to propagate the labels. The ghosted edge approach that I'm going to talk to you about is that the view it takes is that there's actually plenty of labels in the nodes in the network. The problem is that I don't have links to them. So how can I actually make these links, which I did not observe? So these ghost edges are edges where I didn't observe Tina calling Bob, but I'm going to infer that an edge does exist between Tina and Bob because I have some information about the state of Bob. And then if I can properly weigh that ghost edge, then I can find out what the state of Tina is. So we call this teleportation. So as opposed to propagation, like belief propagation, where beliefs propagate through this network, what I'm going to do is I'm actually going to build highways and teleport. We're calling these ghost edges, and teleport the labels. So how does this work, and what does this mean? So the idea with these ghost edges is to increase the number of labeled neighbors for a node. Again, the problem is that you give me a network, I have some labels for some of the nodes, for many of them I don't, and you tell me go and label the rest of them. And I see that because of label sparsity, a lot of the nodes aren't linked to labeled neighbors, and so I want to increase this by these ghost edges. And so the key to success with the ghost edges is to come up with edge weights for them that would correspond to some correlation between the labels of the edge points, right? Because again, I want to have some dependency that's easy to learn. And so now the challenge is that we don't know what the correlation is between the nodes because the labels are missing. So how are we going to approach this? So the way that we're going to do this is we have this conjecture that the correlation is higher between the labels or states of nodes that are closer to one another. And closer means in a graph sense closer, but not in the shortest path in terms of a random walker walking the graph and from time to time coming back to the node of interest. So this idea of random walk with restarts is the same as personalized PageRank. It's been around for a very long time. You have a network. You start a random walker at a node. This random walker walks the graph. So at every node, it randomly picks one of the neighbors, and then from time to time, it jumps back to the original node. If you do this, you're going to hit the stationary distribution, and this corresponds to solving this equation. So basically, if this node 4 is I, so I is equal to 4, I want to find the rank vector for I. So the cardinality of the rank vector of I is all the nodes in the graph. What is the rank vector at time t plus 1, which is equal to the probability that I'm going to just follow the structure of the network, which is represented by this normalized Laplacian. D is the diagonal degree matrix, W is the adjacency matrix. And then whatever the ranks were at time t, plus this is the restart probability. So 1 minus c. And then this vector E is the starting vector where it has zeros everywhere and 1 on the ith node. So you solve this. When you solve this and you hit the stationary distribution, what you get is actually a number, a proximity number, a rank number, in terms of node 4 and all the other nodes in the graph. And if you want to think about it in terms of English words, this rank vector, what it's giving you is giving you close lists of node 4 to another node, and that's a function of 3 things: the number of paths between node 4 here and another node, the length of those paths, and the weights on those paths, right? And so a node that's closer will get a higher proximity value than a node that's further, or a node that's closer, or a node that's further away but has a lot of ways that you can get to it would get a higher value. So, so the standard approach was to learn the dependencies using the labeled data, and success depended on the availability of sufficient labeled data. And now what we have is we have these ghost edges that I'm making, and one way that I can make them is based on this random walk with restart, where I pick a new node that I'm interested in. I will do this random walk with restart, and then when I hit the stationary distribution, I'm going to make these ghost edges to all the other nodes that have a label and weigh them based on the weight in the distribution and the stationary distribution. But one of the other problems was that I have a network where the degree of homophily varies. So network A is very homophilous. All the black people link to all the black people, all the white people link to all the white people. Network B is completely on the other side. The black people only link to the white people, and the white people only link to the black people. And so I want to come up with an approach that can assign or infer labels, states of nodes for both of these. So as opposed to using the original network and having this random walk with restart, what we're going to do is we're going to do an even step random walk with restart. So an even step random walk with restarts is that I'm going to do the same operation as before, except that I'm going to compute the ranks every 2 hops. And so the reason this makes sense is that if I have homophily, then if I jump over you and go to the next person, because it's homophilous, it's okay. I'm like you and you're like him, so I'm going to be like him, right? And if it's anti-homophily, then it's exactly what I wanted to do, right? So I jumped Bob, who wasn't similar to me, and went to Jane, who's similar to me. And because of that, I'm going to get a nice division between all for example, here, the black nodes linking to each other and all the white nodes linking to each other, right? Which is what I want, which is a high relational dependency, which can be used for inference. And so the only difference is in this even step is that you're doing your random walk on the power 2 of the Laplacian. So now that we did this, right, so I had this network, I had some labels, but not too many, and I wanted to know how to label all the other ones, and the idea was let's use teleportation, but how are you going to do teleportation? We're going to do this even step random walk with restart, and generate edges that were not observed, and add weights to them. These weights having correlations will indicate some correlation between the labels of the endpoints. So now what are the actual classifiers? So one of them is this non-learning. There are some cases where you do not need to learn anything. That is, the homophily or the relational dependency is high enough that you do not need to learn. So for this case, it's very simple. You give me your network. What I'm going to do is I'm going to generate ghost edges from the nodes that are unlabeled to the nodes that are labeled. I'm going to get rid of the observed edges. So I'm going to get rid of the fact that Tina actually called Bob. I already utilized that information by making these ghost edges. Then what I'm going to do is I'm going to do just a simple weighted vote of the ghost edges. So, so what's the probability of Tina having class C given her neighborhood is going to be, and her neighborhood now is the links to all the labeled nodes, is 1 over z. Z is just a normalization function, and this is going to sum over all of the neighbors that Tina has that are labeled and how much weight Tina has to that node. And the other approach is the learning approach, where I'm like, well, I don't have this total homophily, so I actually have to learn what the relational dependency is. And so here what we do is that we create the ghost edges just as before by doing an even step random walk with restart. Then what we're going to do is we're going to have to actually learn the dependencies between the class labels of the observed edges and the ghost edges. And so what we do is we actually bin the ghost edges by their proximity score and then learn the dependencies for every bin. So what does this actually mean? It means that if I have a network and I find my ghost edge proximity values, I can draw the distribution of it, and for example, I can cut it into k bins. Here would be 6 bins, and then I'm going to say, okay, put all the ghost edges with the top 3% score in 1 bin. And in some sense, that's like it's its own special observation. Then it's the bin 2, and that's its own special type of observation, so on and so forth until bin 6. So now I started with basically just one type of edge, which was the observed edge, and based on what I said k to, I'm adding k other edge types. And so now I can actually do any kind of learning that I wish to do. We use an ensemble approach, which is a bag of 500 logistic regression classifiers. Here we were only interested in binary classification, so the states are +1 or -1. And now I have this input vector, which would be some features on these different edges that I have. So the observed edge and all the different binned ghost edges. And then I'm going to try to find the optimal weight W for this. And that's going to tell me how to weigh the relational dependencies that I have. And so here it's straightforward. So for each bag, because it's an ensemble approach, you may have heard of random forest. This is similar to random forest. It's just that as opposed to decision trees, we're going to use logistic regression. And so for each bag, we're going to pick a subset of the features, usually log k, k being the number of features. And so the relational features that we use, again, we're not assuming that I have content on the node for privacy reasons or other kinds of reasons that you may think of. So we're going to count the number of neighbors across the observed edges that are plus or minus, and the count of neighbors across the different binned edges that are plus or minus. And so then I can just learn this bag of 500 logistic regression and then see how well I have learned and move on. So just some experiments to ground this, and then I'm going to go more into collective classification. So here's some networks that we looked at. There are other ones that we also looked at. So Enron is the Enron emails in the US. There was this huge fraud case. Enron, an energy company. The task was predict whether an email account belonged to an executive or not. The political books, there's a political books co-purchasing network, and the states are whether the book is neutral or not. Not neutral meaning either conservative or liberal. HepTH is high energy physics, and the topic was whether the paper is a differential geometry paper or not. This is a citation network. And reality mining was an MIT study, and the idea is that whether you were in the MIT study or not, and it's based on phone calls. So the one thing to pay attention to, so V is the number of vertices or nodes in each of these networks. L is the number of nodes that are actually have some labels. These are the core nodes. So there are cases in which even when I have all the information, right, I do not have labels for all of them. And we're going to vary these so we make it even sparser. And then
what is E?
E is number of edges. Number of dyads that you have. Capital V is number of nodes. P is probability. So this I was just going to get to. So the probability of seeing an executive account in Enron is 0.02. So not that many executives in there. The probability of seeing a paper that's based on differential geometry in this HepTH data set is 0.06. Differential geometry, not that popular, at least in this data set. The number of neutral books, or the probability of a book being labeled neutral among the labels that we have is 0.12. And then in reality mining, the probability of being in the study was 0.08. The reason I say this is that there's also this thing of class imbalance. So if you've ever looked at any kind of machine learning problem, one of the things is that you want to have observations from both classes around the same amount. If you have a lot of one class and a lot of the other class, then it's a harder task to learn. A common approach that people use is this approach called SMOTE, and the first author is Nitish Chawla. It was a paper that came out in Journal of Artificial Intelligence Research in 2002, where you undersample the majority class and you add synthetic examples of the minority class.
So what's L again? Can we go back?
So V is the number of nodes. I know, I'm going to get there. I'm going to repeat because there's some confusion. V is the number of nodes I have in a network. So Enron would be, I have 3,081 email accounts. L is, out of this 3,081 email accounts, I only have 1,055 email account that is labeled. So L is the number of nodes that are labeled. E
is the number of edges that I have observed, the number of emails that have been sent between these 3,081 email accounts. Among the L nodes, so among the 1,055 email accounts that I haven't labeled, whether they're executive or not, only 0.02 of them are executives. Questions?
So, but on the right column, there's 100%.
Yes,
labeling.
because they're different data sets. I'm going to modify it.
What's there to inform?
No, because I want to know how hard it would be in this kind of a structure. This structure is different than this structure. As you can imagine, this structure is more bipartite. So what I'm going to do is I'm going to actually reduce the number of nodes that are labeled. I'm going to take away, because I have to run an experiment, right? So if you have had any experience with machine learning, what people do is you give me a data set, it has some label, I will take some labels out, I'm going to put it on my held out test set, I'm going to build a model on the train set, and then I'm going to test it on the test set, right? And I can do this multiple times. Usually people do it tenfold cross-validation, right? That you may have heard of in your statistics classes, right? So that's what I'm going to do, like any good machine learning person. But before I go there, I'm going to show you how much relational dependencies exist in these data sets. And there are multiple ways of measuring this as well, as you can imagine. So the first one that you can imagine is if I give you a network, you would say, I'm going to measure the amount of relational dependency by listing all the edges and counting what percentage of them have the same label on both ends. That's called local consistency. So here, in the Enron, if I list all the 34,000 edges and go through them, see executive, not executive, right? I see that there are 94% where I see an executive linking to an executive. This is very homophilous, right? So executives.
It's among the ages for the known.
Of course, the ones that I don't know, I don't have a phone number of God to tell me what it is. So the other one is HepTH. So if you have a differential geometry paper, it's most likely to cite another differential geometry paper. A differential geometry paper is not going to cite a paper usually that's not differential geometry. Then I have political books, right? And this is also interesting because there's not as many of the neutral books, and because of that, neutral books usually link to a non-neutral book. Again, I list all the edges, these are co-purchasing edges, and I look at them. And I see if they have the same label. And the last one is reality mining, which is the opposite. So if I list all the phone calls in the MIT reality mining data and see if somebody in the study calls another person in the study, as you would expect, that is not going to be the case, that's very popular, right? Usually people in the study call people outside of the study. The other one is relational autocorrelation. This is basically just the Pearson correlation. And so you could do the math. And so for the Pearson autocorrelation, if the number of edges where both classes are the same is less than the number of cases where the classes are different, then it has a minus sign on it. It's minus autocorrelation, negative autocorrelation. The one that I actually like, so I'm giving you a sampling of what people use to measure relational dependency in these networks. The one that I actually like was a Proceedings of National Academy of Sciences paper that came out in 2007 by Park and my colleague Laszlo Barabarsi at Northeastern University, which actually measures dyadicity and heterophilicity. So dyadicity, what it does is it counts the number of edges that connects my zero class to my zero class. Remember, all we're doing is binary classification, so it counts the number of zero nodes that connect to zero nodes, and like any other good physicist, it counts it against what the null model would be, right? What are the number of nodes I have that are zero, and what's the likelihood of them having an edge between them? So n0 choose 2. n0 is the number of nodes whose label is 0. Plus little n11, which is the number of edges that I have that connect a node that's labeled 1 to another one that's labeled 1. And again, I'm going to divide it by how many possible can I have. And then he sums it up, and this is what you get. So that's dyadicity. And then heterophilicity is the reverse, which is I count the number of edges that I have between a node that is labeled 0 and a node that is labeled 1, And then again, I'm going to offset it by what would I expect in a random situation. So they also cared about the direction, so this would be for a directed network. The number of cases where I have where one node is linked to a 0 node, and so on and so on. So this is the log odds of dyadicity versus heterophilicity, and again, the log odds of an Enron executive emailing another Enron executive is very high, and the log odds of a node in the reality mining study, in the study calling somebody outside the study, is very low. So these are some of the ways of measuring how much relational dependency you may have. So the experimental methodology, I already talked about it because there was a question about it, is that, again, this is standard like any other good machine learning or statistician will do. What we're going to do is we're going to vary the proportion of the core nodes that are labeled from 10% to 90%. So 10% of the political books would be I have 10 labeled books, right? Out of my 105, I have 10 labeled books, and out of that 10 labeled books, what I need to do is go back and infer the 95 that aren't. Because I removed the labels for them, right? I need to show that I'm actually doing something. So, and then what I'm going to do is I'm going to do this over 20 trials so that I can then generate this area under the ROC curve. And I'm not using accuracy because obviously accuracy is a bad measure here, right? There is a class imbalance, so if I just were to guess that something is not a differential geometry paper, I will do really well on accuracy. One of the good things about the area on the RC curve is that 50% or 0.5 is a random guess, so you know how well you're doing compared to a random guess. So a lot of this is about sparsity of labels, so the number of training examples will plummet as I remove the labels, right? So here, political books is this black triangle, and at 10% of its core nodes being labeled, I have 10 examples, right? And so you would expect that the learning models will not have enough information to be able to learn. So we're going to try different approaches, and the idea here is, again, would a macroscopic model do better or a microscopic model do better, basically? So we're going to try both the global approaches and the local approaches, both in terms of the non-learning and in terms of learning. And so some of these have collective classification in them, so I'm going to talk about the collective classification among them. So the weighted vote relational neighbor is very simple. You want to know whether Tina is good or bad, you look at its neighbors and you take your weighted vote of the neighbors. This is assuming that the edges have weights. If the edges do not have weights, you assign uniform weights to them. So if Tina has 3 neighbors, this becomes 1/3. I'm going to talk about weighted vote relational neighbor in a plus relaxation labeling in a minute. The Gaussian random field is a semi-supervised approach, which assumes homophily, local homophily, and as we will see, its results are going to be very similar to this WVRN plus RL. And there's a theorem that says that the results are going to be very close. And then this is our approach. And then in terms of the link-based approaches, there's the log forest, which you're just going to use 500 logistic regression models without collective classification, without the ghost edges. And then this one has collective classification in it, and then the ghost edges. So, collective classification, right? So again, as I said, this is a combinatorial optimization problem where I want to label all the nodes in my network at the same time. So not the best label for Tina, but the best label for everybody, and that may mean that it's not going to be the best label for Tina. So what iterative classification algorithm does, and it was stolen from image segmentation, for image segmentation it was that I have this pixel, I want to know what color it is, I'm going to look at the colors of the pixels around it, right? And it's hard labeling, where to find out what Tina's label is, I'm going to ask Tina's friends, and I'm going to assign the most prominent label to Tina, hard clustering. Mean field relaxation is where probability distributions gets passed around. So it's soft and not hard, where it says what's the probability of Tina being fraudulent and what's the probability of Tina not being fraudulent, and that gets passed. And I'm going to go through these in a second. Just seeing how much time I have. So, collective classification, as I said, is a combinatorial optimization problem. I have a set of nodes V, and I'm going to have this neighborhood function N, where it's going to give me the neighbors of a particular node. Here, each V is a random variable, and it can take labels. So far, we've been talking about binary labels, so think about it as fraudulent, not fraudulent, 0, 1, minus 1, 1, whatever is your favorite. And so for some of the V, the set of nodes can be decomposed into X and Y. X is the ones I have labels for, Y is the ones I do not have labels for. And I want to collectively infer the best labels for Y. So what's the iterative classification algorithm is that I'm going to start for every node in Y, which is unlabeled. I'm going to compute a label for them based on only their observed nodes. So these would be their neighbors that have a label. Then I'm going to jump into this loop, and I'm going to repeat this loop until either I reach a threshold or my labels do not change, where I'm going to generate an ordering over my unlabeled nodes. As you can imagine, the ordering over the nodes really matters, which order, because I'm going to propagate this. So every iteration I'm going to come up with a new ordering, and then for each of the nodes, each of the unlabeled nodes in the ordering, I'm going to compute a new estimate. This new estimate is going to be based on the neighbors that actually have a label and the neighbors that now got labels because I'm doing this iteration. So the estimate, so I have a neighbor that doesn't have a label, now it did get a label, and I'm going to use that to estimate what mine is. And I'm going to repeat this. This is fairly simple. The mean field relaxation labeling is similar to that, except that I'm going to pass probabilities around. So I want to know what this node is. I have some probabilities, some guesses over the nodes that I do not know what they are. And then what I'm going to do is I'm going to pass these probabilities around until such time as the probabilities don't change. So I'm going to go through this again. So here I start, I'm going to pass the probabilities around, and that's going to change how much I believe I belong to a class. That's based on this equation. So the probability of an unobserved node I getting class C is conditioned on its neighbors. This 1 over Z is just normalization. I'm going to sum over all the neighbors of node I. I'm going to see how much weight there is between the two neighbors. How much of a best friend are you to me, times the probability of you, my neighbor, having that class condition on your neighbors. And I'm going to do this until the probabilities don't change or I hit a threshold. So it's just whether you pass soft clustering or hard clustering. And you may think, oh, this collective classification really reminds me of guilt by association, and that's exactly what is the case. And so there's this nice paper that came out in 2011 that looks at these various ways of doing collective classification. So this is the random walk with restart. This is semi-supervised learning. This is fast belief propagation. And they compare them based on the matrix formulation of them, where you have some matrix that's a matrix of the topology of the network that's going to guide you. This C is a restart probability. This A and C prime are homophily factors because both semi-supervised learning and belief propagation require them. Then you have your unknowns, and then you have your knowns. This C is the restart probability. So and then you solve this.
Recall what are the coefficient D1, D2, D3?
This is the degree matrix. This is the degree matrix. And A is the adjacency matrix. The reason I mentioned this and I like it is because they're comparing them. You can compare them in terms of mathematical symbols. So exactly what's going on. So just some results since I went through the showing you some of the details about the data sets. Here are the 4 different data sets I showed. Here's the proportion of the core nodes labeled. Here's the area under the ROC curve. Anything 50.5 and lower is random, so higher is better. The black and the pink are the relational learners. These assume that there is a homophily. The red is ours, and the key here is that obviously when there is homophily in the network, we're just as well as the ones that assume homophily. One where homophily doesn't exist, they do poorly, especially as the number of labels increases. But we're able to still stay on top. That is this idea of doing the ghost edges and the weights that we're assigning based on even step random walk with restart seems to do well when you're not going to learn the relational dependency and you have both homophily in some networks and anti-homophily in others. Then the ghost edges is the same structure. I have the proportion of the core nodes labeled. I have the area under the ROC curve. And the key thing to observe is that, for example, as so the blue is us, the green is the log parse with collective classification, and the black is not without the collective classification. And the key is that when they don't have a lot of labeled data, they cannot learn, and so they do not do as well. And so to summarize this one part, I talked about this system. So I have this complex network. It's complex because the topology of it is complex. Very few of the nodes, I know the states. I want to predict the value of the states for all the other nodes. I know how many states I have. Right here, it was just binary. You can extend it to multi-class as well. And so the idea was that what I'm going to do is I'm going to handle label sparsity by increasing the number of neighbors that have labels. And I'm going to do that through these things called ghost edges. And then in terms of dealing with different degrees of relational dependency, what I'm going to do is I'm going to do this even step random walk with restart, which is I'm going to have my random walker walk not the adjacency matrix, but the adjacency matrix times itself, right? The square of the adjacency matrix. And in terms of just a guide to a practitioner who wants to take this, obviously, if you don't have, if you have extreme sparsity in terms of the labels, you cannot learn. So just use a non-learning approach. If you have moderate sparsity and you're not sure about the homophily level, then learn. And then this chart just shows the different classifiers that I talked about. This is average area under the RC curve. These are the ghost edge approaches of actually making these edges that will allow you teleportation. And then these are the rest. And since this is an entanglement conference, I figured I would have something about how I see this relating to what entanglement is. So he said the best possible knowledge of the whole does not necessarily include the best knowledge of all its parts. And in this one particular example that I showed you, it's the comparison between the ghost edges and collective classification, right? Where if I do collective classification, which is I'm looking at the whole and trying to label them, I may not do as good of a job as if I just explore the graph locally and find the correlations that I need. And then, thank you for your information. I do have a postdoc position available in my lab. Some of the things I wasn't able to talk about is how do we embed these graphs and then use them to not just do within collective classification, but across network classification, where I have, let's say, the social network of France and the social network of Luxembourg, and I learn a model in the social network of France, and I want to test it on the social network of Luxembourg. And I'm going to use these graph embeddings to be able to transfer my model without having to have any labels on the social network of Luxembourg. So thank you for your attention, and I'm happy to answer any questions you may have.
The weights on the ghost edges, is it comparable to the average time that another walker would need to go from the one to the other node?
Yes. Yeah, because it depends on the number of paths and the weights on those paths. Exactly. Exactly. It's just that we're changing what the topology should be, right, with the even step. That this is not the right topology. You want the other topology. Yeah. Question?
Yes, so the ghost method, when I was listening to you with this problem of missing information, missing labels, immediately the knee-jerk reaction, in this case as a statistician, would be to use the expectation maximization method. So can you say a word on how the method is positioned? Because I mean, you seem to set the ghost edge and the method as a top performance, but from my knowledge of statistics, it looks like EM would be the best.
Yes, so there are.
Follow-up question is how far do you think the ghost edge method is from reaching the maximum you could expect in order. Of course, it's the top now, but do you expect to improve in the future by additional insight and method and combinations?
So excellent questions, both of them. So there is work on expectation maximization for this particular problem. It was by Jennifer Neville, so one of my slides had a link to her slides, and you can look at that. The problem with expectation maximization is that it can suffer from biases based on the graph distribution during training and then during inference, so during learning and during inference. So some of the work that has been done recently in terms of let's use expectation maximization is to modify the distribution that you get as you go along. That is being cautious with it.
But don't you have the same bias with the ghost method? Because you also use a given lab, which is also biased by your sampling?
No, because the thing is that, so with the ghost edges, it's a one-shot deal, right? With expectation maximization, you keep iterating, right? So, and because of that, the bias is just compound.
Okay.
So,
more powerful because it iterates. So
yeah, but you have to be very careful about the biases.
Yeah, okay.
You have to be extremely, and adjust for them,
Okay.
right, as you go along. And my slides are available online.
So you do say that actually the ghost edge is superior to the EM?
I have not ran tests. So the ghost edges came first, the EMs came second. Jennifer Neville did not compare EM with ours approach. I think from what she looks at it, so hers is this semi-supervised approach with respect to expectation maximization. Ours is what she categorizes as a graph regularization. And so she didn't compare it. I have not compared it. The thing is that if you like EM, you want to use EM, use it, but be careful about the biases. And I refer you to Jen Neville's work on that in terms of how she has a method in terms of entropy to keep track of the bias so it doesn't compound as you iterate.
In terms of future improvements, massive intuition.
Right. It really depends on how sparse both your labels are and your links is, right? So you can imagine, so I just talked about label sparsity, but you can imagine if I have a complex network where the labels are extremely sparse, then I'm not going to get good ghost edges, right? And so then I'm not going to be able to do well. Even with the classification also isn't going to do well, right? Like think about an extreme where no nodes are connected to each other. I have no friendship information, right? I can't do anything that's relational, right? And then you can think about the case where everything's connected to everything. And that's not good at all either, because the relational dependency there, then it becomes harder. So there's this sweet spot of, I don't want to have everything that's unconnected. I don't want to have this everything that's connected. I don't want to have random, because I can't learn with random. So it's this sweet spot that is a function of both the level of link sparsity and label sparsity. But there are no theorems in terms of what would be the best and how far we are from it. Yeah.